Alright, in this video I'm going to review the astronaut self-rescue problem as well as the first problem on billiard balls. And then I'm going to go over the 4 extra collision practice problems. This is all review for your quiz tomorrow, which is going to be on collisions. So for the first problem, astronaut self-rescue, feel free also as I go through the video to skip ahead wherever you need to slow down where you need to. The video I'm shooting for it to take no more than 2 minutes per problem. Maybe that's too ambitious, but 2 minutes per problem for 1 to 6 problems. So the video should be no longer than 12 minutes. Alright, I'm going to go ahead and get started by drawing the situation. So an astronaut in her spacesuit would have a mass of 250 kilograms. She is far from her spaceship and needs to get back. Okay, so she decides to throw her oxygen tank 30 kilograms away from the spaceship to propel her towards the ship. She throws her oxygen tank at 9 meters per second. Okay, so the mass before is going to be 250 kilograms before the separation. And then after the separation, we know that the oxygen tank is going to be thrown. Mass, oxygen tank. And it is going to have a velocity of 9 meters per second. Okay, so before and after, let's just draw what we think is going to happen. We got a little astronaut over here. Wow, that is definitely not a good astronaut. Looks more like an alien than an astronaut. But you know what? Like, aliens are astronauts. I feel like aliens are ancient astronauts, you know? I feel like there's a History Channel documentary about that. Anyway, so we have an astronaut/alien who is hovering. Right now their velocity is 0 meters per second because they're not moving anywhere yet. And they're holding an oxygen tank. Now, after they separate, the astronaut is going to move in some direction opposite of the direction that the oxygen tank is going to move. We just don't know how quickly the astronaut is going to move, and that's what our goal is to figure out. Oh my gosh, this is really bad. I'm so glad I didn't go into art. Alright, anyway. So the momentum for the astronaut, because the astronaut as well as the oxygen tank are both at rest in the beginning, the momentum for the astronaut is 0 roys and the momentum for the oxygen tank is 0 roys. Therefore, the total momentum before is 0 roys. Now, the total momentum afterwards has to be equal to the total momentum before, 30 kilograms.
And we also know that the velocity of the oxygen tank is 9 meters per second, so P is equal to M times V tells us that the momentum of the oxygen tank is going to be 270 roys. We know that in order for this momentum, in order to get a total momentum of 0, whatever this momentum is, the astronaut has to have the exact opposite momentum. That's the only way this works, is if these two added together are going to be 0. Remember, adding these two numbers is always how you're going to find the total before or after, but the difference is sometimes if you have an object moving to the left, it'll be negative. Sometimes if you have an object moving to the right, that'll be positive. In this case, we weren't told that the oxygen tank is moving to, we were not told the oxygen tank is moving to the right, but I assumed that to make the problem a little bit easier. I just said the oxygen tank is moving to the right so that I could write down this positive number and then find the astronaut's velocity based off of, or astronaut's momentum based off of this positive momentum here. So the astronaut has a mass of, their mass was 250 kilograms, but they lost this oxygen tank, and so their mass is now going to be 220 kilograms. This is because their mass of the astronaut in her spacesuit has a mass of 250 kilograms. If they lost this oxygen tank, you can assume the oxygen tank is part of their spacesuit. You could also do this and say that if the you can keep the mass as 250. I wouldn't really mark you down for this because it's not clear whether or not the oxygen tank is part of the spacesuit or not. If I say that it's part of the spacesuit, then the mass is 220 kilograms, and you get P is equal to M times V. V is equal to P divided by M. Negative 270 R over the mass, which is 220 kilograms. Note here you could have also divided by 250. And you end up with a velocity of, go grab a calculator. 270 divided by 220 is going to be 1.22. So the velocity is going to be 1.22 meters per second. You can say this is 1.22 meters per second. And I'm going to leave it like this. It doesn't really matter that this is negative because we don't know which direction the oxygen tank is. And so you can leave it as negative or you can leave it as positive. It really doesn't matter. So 1.22 meters per second. Now, Part C asks us how long does she have to hold her breath if she's 200 meters away from the spaceship. Alright, so we have her velocity. We want to figure out how long, so we know that we're looking for time. So then, to find time and the relationship between time and velocity, we know that v is equal to d over t. And so if we're looking for t, we know that's going to be d over v. The distance is 200 meters. The velocity is 1.22. And so the time it'll take her is around 164 meters per, or 164 seconds. So around almost 3 minutes. That's a long time. 164 seconds. All right. I'm running short on time already. All right. Problem 1: billiard balls. So we have a cue ball moving toward the 8-ball and colliding with it. After the collision, the cue ball stops and the 8-ball continues rolling. Use the law of conservation of momentum to find the velocity of the 8-ball after the collision. Alright, so before the momentum, total momentum depends on just this white ball. And so this has a mass of 1.5 kilograms and the velocity is 3.3. So to find the total, if this is 1.5 kilograms and this is at rest, then this is not contributing any momentum. The momentum here is 0. So to find the total momentum on this side, we know that it has to be mass times velocity, 4.95, positive because it's to the right. Now in this case, the total has to be the same as it is before as it is after, so total here has to also be plus 4.95 roys. You know, however, that this has the same exact mass. Oh shoot, so then the velocity has to be the same as it was here. So P is equal to m times v. V is equal to P over M. In this case, P is 4.95 and M is 1.5. I can do the math, but we already know that it's going to be the exact same. 4.95 as it was before, right? So the velocity is going to be the exact same. We actually don't need to do all this math to figure this out. We can just see, all right, 1.5 kilograms. Velocity 1.5 kilograms at rest. If all of the momentum here goes into here, then it has to have the same exact velocity as it had initially. The only time the velocity is going to be different is if the mass is different, right? Okay, is this collision completely elastic? Is kinetic energy conserved? Prove. The only way you can show if kinetic energy is conserved is if the kinetic energy before is the same as it is afterwards. Now, that means that whatever this number is has to be equal, whatever amount 1/2 mv squared is before has to be equal to 1/2 mv squared afterwards. So we already know that the mass stays the same. We don't even need to do this calculation.
To see that it is going to be conserved and it's going to be the exact same. We don't have to multiply these numbers out. So yeah, the collision is completely elastic because the total kinetic energy, which depends only on this ball moving, is going to be the same as the total kinetic energy, which depends only on this ball moving. The mass is the same and the velocity is the same. There are situations where this might not be true. I won't be asking you how to do that on your quiz tomorrow though. Alright, so let's take a look at the extra collision practice problems. I'm going to try and finish this up in, oh my gosh, we're already at 9 minutes. Woo! Alright. We got a fender bender, and take note that there are answers right after each problem. We got a fender bender. So 303 kilogram car is driving 40.5 meters per second on a city street. The car collides with a 515 kilogram truck traveling in the same direction at 20.3 meters per second. Same direction. After the collision, they are stuck together and move forward with the same velocity. Okay. I'm going to draw in my negative and plus, and I'm going to draw in the car. This is a car. car. And we'll draw the truck in yellow. This is a truck. Boop, boop. Truck. So the truck has a mass of 515 kilograms and a velocity of 20.3 meters per second. The car, on the other hand, has a mass of 303 kilograms and a velocity of 40.5 meters per second. They're both traveling in the same direction, so their momentums are going to both be positive and going to add because they're both going this way. So what I'm going to do, total momentum before, because I didn't give you the little boxes, and I'm not going to give you the little boxes on the quiz either. But you know that these two objects are moving separately. The momentum of the car is going to be 303 times 40.5, which is 303 times 40.5 is 12272 roys. Momentum of the truck is going to be 515 times 20.3, which is going to be 10,455 roys. The total is going to be those two added together. So 12,272 plus 10,455. So the total before is going to be something like 22,727 roys, and that is going to be the same exact amount as it is going to be afterwards. So 22727 roys. Now we know after the collision, both the truck and the car stick together. So they're going to be moving together, and the car is going to be a little creaked up because it just got smushed by that truck probably. But in any case, they're moving together. We don't know what their velocity is, but we know that their combined mass is going to be equal to the sum that we have here, 303 plus 515. Their mass can only be whatever their total mass can only be whatever the individual masses are added together, 818 kilograms. Now we have the momentum, the total mass, and we want to figure out the combined velocity. Easy money. P is equal to m times v. We want to figure out the velocity, so we divide this by m, divide that by m, and then we do some algebra, and we end up with 22727 r divided by, wow, that's a lot of twos, divided by the combined mass, which was 818 kilograms. That gives us a velocity of 22727 divided by gives us a velocity of around 27.7, or we could say 28 meters per second, or 27.8. Oh shoot, I should have rounded to, well, whatever. So I got 27.8, or let's see here, it says 27. Be clear, it says 27.78, which is basically 27.8 or 28. Alright, now the one below, Superman and the bus. That's not Superman. I don't even know what I'm doing anymore. Alright, so we got Superman. He's got the red S, right? The iPhone S, the red iPhone S. No. JK. He's holding a bus. It's actually the truck from the last problem. Now, initially, Superman is hovering in midair holding a bus, okay? Superman is allowed to break the laws of physics once per day, obviously, because he's Superman. He throws a bus 987 kilograms to the right at 300 meters per second. If Superman has a mass of 90 kilograms, what velocity does he move with after he throws a bus? Alright, so we have some information about what he's doing before and what he's doing after. Now, we know that he throws the bus, and then after the bus is thrown, we have some information. This is just like the separations problem. Actually, this is a separations problem. We have a bus being thrown, and we know that if the bus is thrown that way, then Superman also has to go the other way in order to conserve momentum.
The exact amounts we don't quite know yet. So let us do some math and figure out what the devil is going on here. Alright, so if Superman's hovering in midair holding this bus, in the very beginning the bus is going to be hovering, Superman's going to be hovering, they're not moving, so their velocity is going to be 0 meters per second. If their velocity is 0 meters per second, then it does not matter what their mass is combined, right? So the total momentum before has to be 0 roys. Total momentum before, if it's 0 roys, also has to be 0 roys after the collision or the separation. In this case, this bus has 987 kilograms of mass. It has a velocity of 300 meters per second. Now, if we know that to be true, then we can find its momentum pretty easily, because we have a bus of 987, whoopsie daisy, 987 times 300 meters per second. So that's 296,100. So the momentum for the bus is equal to 296,100 roy. Now, here's the thing. The bus has a momentum in the positive direction. Note, the bus is going to the right, so that I made that positive. But in order for the total momentum to be 0, that means that whatever momentum Superman has to be exactly the opposite of whatever the momentum the bus has. So we'll say that P Superman, P sup Superman, saw dude, has to be negative 296,100 R. Now that means that if we have the momentum of Superman, we have his mass right up here, it's 90 kilograms, we can find his velocity, because P is equal to M times V, V is equal to P divided by M. We have the P, I'm going to plug this in my calculator, and we're going to divide it by the M. So the P is 296,100. Oh, forgot a negative. And the M is going to be 90 kilograms. Right? So his velocity is going to be negative 3,290 meters per second. This could also be 3,290 meters per second to the left, so in the left direction. So you can leave it as negative or say to the left, because we assume that left is negative, right is positive. Alright, on to the next one. Hans! Broken blaster. Oh, love Han Solo. Alright, Han Solo is in a shootout with Greedo, the bounty hunter. Who shot first? We don't know. Han's blaster gets hit by a blast and cannot fire anymore. Han sees that Greedo is near the edge of a cliff. Oh man, there's a lot going on here. Greedo is near the edge of a cliff. Han throws his blaster as hard as he can, 25 meters per second at Greedo. The blaster hits Greedo and Han's blaster stops completely. What is Greedo's velocity after he gets hit by the blaster? Alright, Greedo, the alien, is standing on a cliff, on the edge of a cliff. Han Solo's blaster is coming out of nowhere. Pa-chew, pa-chew. It's flying towards him. We know that Greedo is standing here. He's near the edge of the cliff, but he's not moving. It doesn't give us any information about whether or not he's moving. So we can assume that Greedo's at rest. We also know that Greedo has a mass of 67 kilograms, so I'm just going to write this in here. Now, the blaster is coming in hot at 25 meters per second. We also know the blaster has a mass of 1.6 kilograms. The blaster is the only thing that's moving in the beginning, so the total momentum is based off of the momentum of the blaster. So P blaster is equal to its mass times its velocity, 1.6 times 2.5, so that's 40 R's, and we'll say positive, negative, negative, positive as we do. So we know that the only thing that's moving in the beginning is the blaster and has a momentum 40 roys. So the total momentum before is 40 roys. Law of conservation of momentum, whatever comes before has to come after. And now we know that all of the momentum of the blaster went into Greedo. We know that Greedo's going to start moving. Whoa, Greedo, no! But we don't know how fast he's going to move. You know his momentum has to be 40 roys, right? Because we know at this point the blaster stopped completely. So the blaster isn't actually moving to the right anymore. It has a velocity of 0 meters per second. And so this actually has no momentum. So it doesn't matter what its mass is. The blaster doesn't have any momentum. The only thing that has momentum is Greedo. And if Greedo has a mass of 67 kilograms and he has some velocity, we don't know what that is, so we can do some calculations. P is equal to m times v. V is equal to P over m. In this case, P is 40 roys. In this case, m is 67 kilograms. We can see that Guido's velocity has to be 40 divided by 67, around 0.59 meters per second. Is that enough to knock him off of the cliff? I don't actually know. We don't have enough information to say. Guido. Guido.
Alright. Now. Oh, there's a dude. Triple T. Terrible Terry Tate. He's back at it again with the as the office productivity enforcer. Trip T sees an office worker 50 kilograms who is hanging out by the water cooler 2 minutes past her break ending. Oh no! Office worker, bad idea. If he launches himself at her with a velocity of 6 meters per second to the right while she's standing at rest, what is their combined velocity if they stick together after the collision? Alright. Oh boy. Terry Tate. He launches himself at her with a velocity of 6 meters per second to the right while she's standing at rest. Okay, so she's standing at rest. Oh, and she's standing by the water cooler. Bad idea, especially when you have work to do. She's standing by the water cooler. Triple T is coming out of nowhere. It's coming in hot. So Trip T has a mass of 135 kilograms and a velocity of 6 meters per second. It's going to be positive because he's moving to the right. The office worker has a mass of 50 kilograms, but in the beginning she's at rest. So what's her velocity? 0 meters per second. That is correct. Now that means that all of the momentum in the beginning of the problem is coming as a result of Terrible Terry Tate's mass and velocity. So his mass is 135, his velocity is 6 meters per second, his momentum is 810 roys. It's 810 roys before, it has to be 810 roys after, and so if they stick together, Triple T. Wow, this is a really poor drawing. I keep saying that. I should be more confident in my drawings. They're moving together, then their combined mass, you have to look at their combined mass because they're sticking together, right? So their mass together is going to be 135 for Terry Tate plus 50 for the office worker, so that's 185. You don't know what their velocity is, but you know what their combined momentum is. Once again, we're back at it again. P is equal to m times v. V is equal to P divided by M, and so V is going to be equal to P, which is 810, divided by M, which is 185. So we can see that the velocity is going to be around 4.4 meters per second. Alright, so these are the types of problems that you'll see on your quiz tomorrow. I went over 6 different types of problems today. 4 of the review problems and then 2 of the problems in your collisions packet. Let me know if you have any questions. Good luck studying. Have a blessed day.